ठीक है.
आवाज से भाई.
हाँ हाँ, यस यस यस. ठीक है ठीक है. सो yes. So I hope that my slides are visible to you. Okay. So yesterday we have covered the part of the refrigeration and the refrigeration cycle. Now today we are going to discuss the air standard cycles in this 2 hours of lecture. So we will start with the air standard cycles and yes. So it is the under the subject of the engineering thermodynamics and air standard cycles. You have to study in the subject of the engineering thermodynamics, and you might have also come across the various subjects which is based on the air standard cycle or the thermodynamics. The subjects like heat transfer, subjects like your basically the we can say the IC engine, then the gas turbine, and then the heat transfer. So the thermal engineering subject, these are based on your engineering thermodynamics. And as you are aware that the air standard cycles and its study is very important. So you might have seen that we have drawn the such kind of cycles basically in a PV diagram, that is pressure volume diagram, and the TS diagram, that is the temperature entropy diagram. So in this pressure volume and the temperature entropy diagram, we study the heat interaction between the inside the system, how it is being happening and how it is being done. So therefore, this is one of the important topic as far as our GATE curriculum is concerned, and you may find several questions based on this particular topic. So, what we are going to study today, you can see that the engine block is shown to you, which means that the applications of the air standard cycles like auto cycle, diesel cycle, or the dual cycle, it is in the IC engine application. So we are going to study today the introduction, the air standard cycles, then auto cycle, thermodynamic analysis of air standard auto cycle, then diesel cycle, thermodynamic analysis of air standard diesel cycle, then dual cycle, thermodynamic analysis of air standard dual cycle, and the comparison of auto cycle, diesel cycle, and the dual fuel cycle. So the three thermodynamic analysis of the engine, that is ideal gas cycle, which is called as the air standard cycle, that is idealized processes, and then idealized working fluid, then fuel air cycle, that is idealized processes and the accurate working fluid model. And third thermodynamic analysis is nothing but the actual engine cycle. So in the actual engine cycle, the accurate models of processes, accurate working fluid model. So the operating cycle of an IC engine can be broken down into a sequence of separate processes. For example, the intake, compression, combustion, expansion, exhaust. These are the cycles basically which is being followed in the four-stroke engine or the two-stroke engine, like processes like a intake, okay, that is taking the intake fresh air into the combustion chamber, then compression of the that is mixture or compression of the air which is taken inside the combustion chamber, then ignition and the combustion which is happening inside the chamber, and then expansion, or we can say the power stroke which is being obtained through the combustion of the gases, and then the exhaust, removing the gases from the cylinder into the atmosphere. So which means that whether it is a two stroke or the four stroke, the cycles like intake, compression, combustion, expansion, and the exhaust, these are the similar one. If you consider the crank position and the piston position, it is being shown. So in the first figure, you can see that the inlet valve is in the open condition and exhaust valve is in the closed condition, and gas and air moisture from the carburetor which is being sucked inside the cylinder from the carburetor, which means that it is a particularly the example of the SI engine, spark ignition engine. In case of the compression ignition engine, the intake to the combustion chamber through the intake manifold is nothing but the air. Okay, and then air is compressed in the second cycle. So this part is nothing but the connecting rod. This is nothing but the crankshaft which is rotating through the 360 degree, and under this 360 degree revolution of the crankshaft, what we can see here, now the both the valves are closed. So when the both the valves are closed, then when the piston moves from the bottom dead center toward the top dead center, there is a compression of the charge which is being taken inside in the earlier cycle, and this charge will get compressed. So if it is a gas air moisture from the carburetor in a SI engine, if it is it is a CI engine, compression ignition engine, in that case only the air suction will be there and air will be compressed. Then here, the at the end of the compression stroke or the compression cycle, the spark plug is provided in the spark ignition engine, and the spark is produced at the end of the stroke, and then the ignition which is being taking place for the air fuel mixture which is taken inside the combustion chamber. And then okay, we get a expansion of the gases is being taking place, because burning of the charge which is being compressed inside the cylinder, it is being taking place, and we get a power stroke, means power cycle here. And under this condition also, both the valves are in the closed condition. Okay, and this power which is being produced due to the combustion, due to the ignition of this fuel air charge which is compressed inside the cylinder, further, we this is being moved. It exert pressure onto the piston, and this crank starts rotating. Now here in the exhaust stroke, what happens when again the piston start moving from the top dead center to the, sorry, bottom dead center to the top dead center, the exhaust valve is in the open condition, and the exhaust gases, means combust gases which are burned inside the combustion chamber, they are forced to move out of this exhaust valve into the exhaust pipe, and through the exhaust pipes or the silencer, it is exhausted to the atmosphere. So in nutshell, we can say that the basically the cycles or the processes which is being taking place inside the IC engine is nothing but the intake of the gas air moisture, gas air mixture from the carburetor, okay, which is supplied by the carburetor in the SI engine. Then it is compressed in the cylinder, okay, with the help of the this reciprocating piston and cylinder arrangement. Then both the valves are in closed condition, and spark is being produced at the end of this compression stroke, and further ignition of the fuel which is being taking place inside the cylinder. Because of this ignition, the expansion of gases is being taking place, and we get a working stroke which is also called as the power stroke. And then again, in the last stroke or in the last cycle, the exhaust gases which are burned inside the cylinder, these are exhausted to the exhaust pipe and then into the atmosphere. So this is the functioning or the working of the basically the IC engine. So the cycles which is being followed, because we are today going to study the cycle, what is the importance of the cycle, and how it is there, how would the is burning, how this IC engine is being functioning. So actual IC engine does not operate on ideal thermodynamic cycle that are operated on the open cycle, which means that the actual cycles are the ideal cycles, and they are not practicable. So there will be certain change will be there. The accurate analysis of IC engine process is very complicated to understand it well, and it is advantageous to analyze the performance of an idealized closed cycle, which means that the knowledge of the theoretical cycle and the practical cycle is being required to analyze the engine performance and to better go with the design of the basically this kind of IC engines. So air standard cycles differ from the actual by the following method. What is the difference in the actual cycle and the air standard cycle? That is, a gas mixture in the cylinder is treated as air for the entire cycle. However, the mixture of air and the fuel is there, which is supplied from the carburetor. So it is considered as the treated as the air for the entire cycle, and property walls of air are used in the analysis. The real open cycle is changed into a closed cycle by assuming that the gases being exhausted are fed back into the intake system. Then the third one, the combustion process is replaced with the heat addition term, which is called as the Q in of equal energy value. The open exhaust process, which carries a large amount of enthalpy, is denoted by Q out of the equal energy value. So then actual engine processes are approximated with the ideal processes. So the almost constant pressure intake and exhaust strokes are assumed to be constant pressure. Then the compression stroke and expansion strokes are approximated by the isentropic processes. The combustion process is idealized by a constant volume process for the SI cycle and a constant process for the pressure process for the CI cycle, means compression ignition cycle, or a combination of both, which is called as the CI dual cycle. Exhaust blowdown is approximated by a constant volume process. All processes are considered reversible. So this is the assumptions basically approximated with the ideal processes, and almost all constant pressure intake and exhaust strokes are assumed to be constant pressure. Now we will go into the details of these fundamental laws which is being used now in our analysis for the air standard cycle. So for an ideal glass, the volume is directly proportional to the Kelvin's temperature if modes of the gas or pressures are constant. Now here look at this one. This is the Charles law. So 65 degrees centigrade, here the 250 degrees centigrade. So what the Charles law says? Charles law says that V1 by T1 is equal to V2 by T2, because when pressure is constant, this equation is used to compare the different conditions of the same substance. So temperature is directly proportional to the volume, and V by T is equal to K, that is constant of proportionality. So volume divided by temperature equals to the K constant, where K is the coefficient proportionality constant. So Charles law suggests that V by T is equal to K, V by T is equal to constant. So V volume, T temperature. So we can say that V1 by T1 is equal to V2 by T2. Then the Gay-Lussac law, the pressure of an ideal glass is directly proportional to the Kelvin temperature of the gas if the volume and moles of the gas are constant. So as per this Gay-Lussac law, which we can see that P1 by T1 is equal to P2 by T2. So when volume is constant, this equation is used to compare the different conditions on the same substance, which means that pressure is proportional to the temperature. In earlier case, we can see that temperature is proportional to the V volume, and in this case, as per this Gay-Lussac law, the P is proportional to the T, means pressure is proportional to the temperature. Therefore, the P by T is equal to constant. So pressure divided by temperature equal to the constant, and which we can written it as a P by P1 by T1 is equal to P2 by T2. So decrease temperature, decrease pressure, increase temperature, increase pressure. Then ideal gas law, okay, which you have already studied ideal gas law in the physics subject in 7th, 8th, 9th class. So what is the ideal gas law? The combining the Boyle's law and the Charles law allows for developing a single equation. So what is that single equation? Because what the this Charles law says, that is V by T is equal to constant. Another says that P by T is equal to constant. So therefore, the by combining these both the laws, that is Boyle's law and the Charles law, it allows us to develop a single equation, and this single equation is nothing but PV is equal to RT. So where the constant of proportionality is nothing but the R, the gas constant. So the gas constant R is different from each gas, and it is to be determined from the equation like R is equal to RU by M. So what is RU here? RU is the universal gas constant, and M is the molar mass, molecular weight. So therefore the PV is equal to RT. Okay, this is the ideal gas law. By combining the Boyle's law and the Charles law, we are getting. During the expansion and the compression pressure and volume are processes, they are also often related by the PV to the power of n is equal to constant. So P is nothing but pressure, V is nothing but the volume. So PV to the power of n is equal to constant, or P is equal to C into V to the power of minus n. Just by rearranging the term, you can remember it. You can learn it in any way. So PV to the power of n is equal to C, where C is constant and n is a value between 1.0 and the 1.4. So assuming the combustion chamber is perfectly insulated, the adiabatic, that is n is equal to K, and K is equal to 1.4 for an isothermal process, n is equal to 1.0. So PV to the power of n is equal to C, and for an isothermal process n is equal to 1. Okay, and for adiabatic process n is equal to, that is K is equal to 1.4. So this is nothing but the polytropic process. Then the isentropic process, for ideal gas K is constant. Vedant. So PV to the power of K is equal to C. PV to the power of K is equal to C. So therefore P2 by P1 is equal to V1 by V2 to the power of K. So using the equation of state for ideal gas, that is PV is equal to MRT. So TV to the power of K minus 1 is equal to CD. Or Tp to the power of 1 minus K divided by K is equal to C. Then isentropic work done during the isentropic process become the W is equal to integral of 1 by 2 1 by 1 to 2, that is PdV is equal to integral of 1 to 2 CV to the power of minus n dV is equal to C into V2 to the power of minus 1 minus V1 to the power of minus n plus 1 divided by minus 1 is equal to, work done is equal to P2 V2 minus P1 V1 divided by 1 minus 1. This is nothing but the isentropic work, that is work done during the isentropic process. For an ideal gas, this equation can be written as, that is P is equal to rho RT, dH is equal to Cp dt, and du is equal to Cv dt. So therefore, then W is equal to are in bracket T2 minus T1 divided by 1 minus K. Then specific heat constant, that is when analyzing what occurs when within the engines during the operating cycles and exhaust flow, the following air property values are being used. So value of the Cp is equal to 1.108 kilojoule per kg Kelvin, Cv is equal to 0.821 kilojoule per kg Kelvin, K is equal to Cp divided by Cv is equal to 1.108 divided by 0.821, 1.35, and R is equal to Cp minus Cv, universal gas constant is equal to 0.2887 kilojoule per kg Kelvin, or otherwise R is equal to 287 kilojoule per kg Kelvin. So you need not have to remember these values of the basically Cp, Cv, K, and R, but it will be given in the whatever the numerical is there, that which values you have to use. Then air properties. For processes such as inlet flow in superchargers, then the turbochargers and the carburetors, and airflow through the engine radiator, the following air properties values are used. Okay. Now, in the subject of IC engine, okay, we use this supercharger, turbochargers, and carburetors. So we use the superchargers, turbochargers, and the carburetors, and airflow this engine radiator, because you are aware of the devices which is being used like a supercharger, turbochargers, and the carburetors. So the values of the CP is being given by 1.005 kilojoule per kg Kelvin. CV is equal to 0.78 or 718 kilojoule per kg Kelvin. K is equal to Cp by Cv is equal to 1.4, and R is equal to Cp minus Cv 0.27 0.287 kilojoule per kg Kelvin. Now let us begin with the first cycle in our study. Auto cycle. So look at this PV diagram and the temperature entropy diagram. So this cycle is nothing but the auto cycle. In the PV diagram, you can see here 1 to 2, okay, section 2 to 3, basically the compression where the pressure is increased, then the 3 to 4, okay, the expansion, 4 to 1, the exhaust. So here in the temperature entropy diagram, that is 1 to 2 is nothing but the suction, 2 to 3 is nothing but the compression, 3 to 4 is the power stroke, and 4 to 1 is the exhaust stroke. So this is the auto cycle. So in the auto cycle, you can see here the 6 to 1, 6 to 1 is the intake. So what is happening here? 6 to 1 is the intake, 1 to 2 is the isentropic compression, 1 to 2, and 2 to 3 is constant volume heat addition. So this process 2 to 3 is nothing but heat addition process, that is constant volume heat process. And then point 3 to 4 isentropic expansion. So 3 to 4 isentropic expansion, 4 to 5 blowdown. Okay, 4 to 5 is there, the blowdown is there, and 5 to 6 is the exhaust. So we can see that the ideal Otto cycle, it consists of the two isentropic processes, that is isentropic compression and isentropic expansion, and the two constant volume process, like a constant volume heat addition, okay, constant volume heat addition, and constant volume exhaust means the blow down process. So this is the future of the Otto cycle. Then intake strokes. So we know that the intake stroke of an engine, it starts with the piston is at the TDC. What do you mean by the TDC and the BDC? TDC is nothing but the top dead center of the top dead center of the engine, and BDC is nothing but the bottom dead center. So the constant pressure processes at inlet pressure of 1 atmosphere. In real engine, process 6.1 will be slightly less than the atmospheric due to the pressure losses in the inlet of the airflow. So the temperature of the air during the inlet stroke is increased as the air passes through the hot intake manifold. So you can see here, this is the intake process which is going on, that is 6 to 1 filling of the cylinder. Then the compression stroke in an isentropic compression from BDC to TDC, that is process 1 to 2. Here you can see that BDC to TDC, process 1 to 2. This process will be there. In real engine, the beginning of the stroke is affected by the intake valve not being fully closed until slightly after the opening of the spark plug before the TDC. And in addition to increase in pressure, there is also increase in temperature due to compressive heating. So this is about the compression stroke which is being carried out in the process 1 to 2 when the piston moves from the BDC to TDC. Then the third process in the Otto cycle is nothing but the combustion process. So combustion process, it is a constant volume heat input process, that is 2 to 3 at the top dead center. So here you can see the four strokes of the engine, that is intake stroke, then compression stroke, then power stroke, and then finally the exhaust stroke. The power stroke is shown in the red color, where the expansion of gases due to burning, the expansion of gases is being taking place, and we get basically the work done during this stroke. So therefore, it is pushing the piston in the downward direction, and this is what we say that where the flywheel is coming to the picture, because in case of the four stroke engine or even in case of the two stroke engine, the what happens, the power stroke is only in the one cycle for some duration of the degree for some duration of the piston movement. So therefore this power should be utilized for another three strokes, like an intake stroke, compression stroke, and the exhaust stroke. And the that is rotation of the crankshaft should be smooth, okay, and it should operate at the same speed. So therefore, okay, the flywheels are also being used in the IC engine. So combustion process, it is a constant volume heat input process 2 to 3 at the TDC. In real engines, the combustion starts slightly to by the TDC reaches its maximum speed near the TDC, is reached at point 3 by the cylinder. So again here the processes on the Otto cycle, in the Otto cycle you can see that volume, pressure, here intake stroke, okay, compression, adiabatic compression, then 2 to 3 heat addition at the constant volume, then adiabatic expansion, which is a power stroke. At this point, point 3 ignition is taking place, and this is a power stroke. adiabatic expansion, and then 4 to 1 is nothing but the exhaust stroke or blowdown, which is being considered as an exhaust stroke. So this is the processes in the basically the auto cycle. Then the power cycle, power stroke or the expansion stroke in a auto cycle. So high pressure on the piston phase forces the piston back toward the BDC and produces the work and power output of the engine. So the power stroke of the real engine cycle is approximated with an example of the Otto cycle. The beginning of the power stroke is affected by the last part of the combustion process, and at the end of the power stroke, it is affected by the exhaust valve being opened before the BDC. Values of both the temperature and the pressure within the piston decrease as volume decreases from the TDC to BDC. So this is the power stroke. Then let us look at the another two stroke, that is exhaust blowdown. Let me check whether it is going on correctly or not. Yes. So exhaust blowdown, that is exhaust valve is open near the end of the power stroke, means when the power stroke is being completed, the exhaust valve it opens. A large amount of exhaust gas is expelled from the cylinder, reducing the pressure to that exhaust manifold, and the exhaust valve is opened BDC to so the exhaust valve is opened BDC to allow for blowdown to occur, and the auto cycle replaces the exhaust blowdown open system process of the real cycle with a constant volume pressure reduction. The closed system process 4-5. Enthalpy loss during this process is replaced with heat rejection in the engine analysis. And the final stroke is nothing but the exhaust stroke occurs as the pistons travel from the BDC to TDC. Okay, and process 5-6 is the exhaust stroke that occurs at a constant pressure of 1 atmosphere due to the open exhaust valve. Then thermodynamic analysis of the air standard cycle, that is process 6-1 is a constant pressure constant pressure intake. So process 6-1, that is constant pressure intake of air at PO, and intake valve opens and exhaust valve is the close. So P1 is equal to P6 is equal to PO. So W6 minus 1 is equal to PO in bracket V1 minus V6. Then all valves close, that is T2 is equal to T1 into V1 by V2 to the power of K minus 1 is equal to T1 in bracket V1 minus V2 K minus 1, and therefore T1 is equal to RC to the power of K minus 1. Then P2 is equal to P1 into V1 by V2 to the power of K, is equal to P2 is equal to P1 into V1 by V2 to the power of K So P1 is equal to RC to the power of K. Q is equal to 1 to 2, 0. So work done, isentropic compression stroke work done, that is W12, mm, that is P2V2 minus P1V1 divided by 1 minus K. So R is taken outside, then the T2 minus T1 divided by 1 minus K is equal to U1 minus U2 is equal to CV in bracket T1 minus T2. So process 2 to 3, that is constant volume heat input combustion. So all valves are closed, that is V3 is equal to V2 is equal to VTDC, W23 is equal to 0. So Q23 is equal to Q in MF QHV NC is equal to MMCV in bracket TC by T3 minus T2. So MA plus MF in bracket CV is equal to T3 minus T2. So whereas T3 is equal to T max and P3 is equal to P max, and the Q23 is equal to Q in, that is heat in, is equal to CV in bracket T3 minus T2 is equal to U2 minus U3 minus U2. So this is the constant volume heat input combustion process. Then process 3 to 4, isentropic power or the expansion stroke. So isentropic power or the expansion stroke, that is this process is nothing but Q3 to 4 is equal to 0. So therefore the T4 is equal to T3 in bracket V3 by V4 to the power of K minus 1, and T3 is equal to V3 into V3 by V4 to the power of K minus 1. So therefore is equal to T4 is equal to T3 in bracket 1 by RC to the power of K minus 1. Then and the P4 is equal to, that is P3 into V3 by V4 to the power of K minus 1, P3 in bracket V3 by V4 to the power of K minus 1, and finally P4 is equal to P3 in bracket 1 by RC to the power of K minus 1. So work done in the isentropic power or the expansion stroke, W34 is equal to P4 V4 minus P3 V3 divided by 1 minus K is equal to RT4 minus T3 divided by 1 minus K, where this W34 is equal to U3 minus U4 is equal to CV in bracket T3 minus T4. Then the constant volume heat rejection process, which is the exhaust blow down process. So here in this case, the exhaust valve it opens and the intake valve is in the closed condition. So here in this case, it is a constant volume process. So therefore, V4 is equal to V5 is equal to V1 is equal to VBDC, bottom dead center, and work done 4 to 5 is 0. So Q45 is equal to Q out is equal to MMCV in bracket T5 minus T4 is equal to MMCV T1 minus T4, and then Q45 is equal to Q out is equal to CV T5 minus T4 is equal to U5 minus U4 is equal to CV into T1 minus T4. Then constant pressure exhaust stroke, which is at the PO. So exhaust valve open and intake valve close. So therefore P5 is equal to P6 is equal to PO. So W56 is equal to PO in bracket V6 minus V5 is equal to PO into V6 minus V5. So therefore, thermal efficiency of the Otto cycle is nothing but the work done divided by the work input. So therefore, the efficiency of the Otto cycle is given by W net divided by heat addition, that is Q in, is equal to 1 minus Q out divided by Q in. So therefore, the efficiency of the Otto cycle is being given by the equation 1 minus CV in bracket T4 minus T1 divided by the CV T3 minus T2, and finally the the equation of the thermal efficiency of the Otto cycle is 1 minus in bracket T4 minus T1 divided by T3 minus T2. So thermal efficiency of the Otto cycle, that is for isotropic expansion and compression and expansion stroke, and recognizing that V1 is equal to V4 and V2 is equal to V3. Further, the equation can be modified as T2 by T1 is equal to V1 by V2 to the power of k minus 1, V3 by V4 to the power of k minus 1, again equal to the T3 by T4. So T2 by T1 is equal to V1 by V2 to the power of k minus 1 is equal to V4 by V3 to the power of k minus 1, and also it is equal to the T3 by T4. Okay. So rearranging these terms, we get T4 by T1 is equal to T3 by T2. So rearranging this equation of the Otto cycle, that is 1 minus T1 by T2 in bracket T4 by T1 minus 1 divided by T3 by T2 minus 1. So the thermal efficiency of the Otto cycle, the equation becomes Otto cycle is equal to 1 minus T1 T2. So combining these equations, that is T2 is equal to T1 in bracket V1 by V2 to the power of k minus 1. Then T2 is equal to T1 into V1 V2 to the power of k minus 1 is equal to T1 into RC k to the power of minus 1. So efficiency of the Otto cycle is equal to 1 minus 1 by V1 by V2 to the power of gamma minus 1. So therefore, efficiency of Otto cycle, thermal efficiency is given by the equation 1 minus 1 by RC to the power of 1 by k minus 1. So Otto cycle, then we will see the processes and other characteristics of the Otto cycle as a air standard cycle. So let me check whether it is going on or not. Okay, yes, going on. So we will take a 1 minute break, biological break, and then we will continue. So the Otto cycle, that is a spark ignition compression ratio limited by the T3, that is auto ignition, and P3, that is material strength. Auto cycle is around 56%. So cylinder temperature varies between the 300 Kelvin to the 2000 Kelvin. So 1.2 is lesser than the 1.4 is, let's say, and K is equal to 1.3 most representative. So here the compression ratios you can see that 2, 4, 6, 8, 10, 12, and 14, and the efficiency of the auto cycle, that is point 0.1, point 0.2, point 0.3, point 0.4, point 0.6, and this is the typical compression ratio for the this is the indicated efficiency and the specific you do the heat addition by 2 to 3, then again it will increase. So therefore MEP, that is the MEP, that is W divided by V1 minus V2 is equal to Q in divided by Q1 in bracket RC divided by RC minus 1 into the that is efficiency of the auto cycle. So MEP is nothing but the mean effective pressure, which is MEP divided by P1 is equal to W divided by in bracket P1 in bracket P1 minus P2. So Q in divided by P1 V1 in bracket, that is RC divided by RC minus 1 into efficiency of the auto cycle. Then auto cycle, the thermal efficiency of the auto cycle depends on the specific heat ratio. So the ratio you can see here, this is increased efficiency and compression ratio versus the increased effective pressure. So as expected, the indicated mean effective pressure IMEP depends on the heat addition. Mean effective pressure is equal to efficiency in Q in divided by MRT1 divided by 1 by minus 1 by RC. Therefore, and the equation is V1 is equal to M into RT1 divided by P1. So non-dimensional MEP with the P1, what we get, that mean effective pressure divided by P1 is equal to thermal efficiency in bracket 1 divided by 1 minus 1 by RC into Q by RT1, and R is equal to C. So MEP divided by P1 is equal to thermal efficiency Q by CVT1. So MEP by P1 is a function of heat added, initial temperature, compression ratio, properties of air, namely CV. So MEP by 3 P3. So MEP by P into 1 by Q2 divided by CVT1 RC to the power of gamma minus 1 plus 1. Okay. So the closing thoughts on the basically the auto cycle efficiency serves as an upper limit to the efficiency of is never achieved. This theoretical analysis is flawed in that it ignores the friction and the heat transfer. So these are the closing thoughts of the auto cycle. Let me check whether the time is there or not. Otherwise, we will close down today and with this lecture of auto cycle. Okay. So PV diagram, pressure volume diagram of an SI engine. We have seen the auto cycle, and under this cycle now, this is your what we can say the volume, P pressure on the y-axis. So it is a PV diagram, and this portion is nothing but the displacement. Okay, displacement and inside the cylinder, and this particular portion is the clearance is provided in the IC engine, because it consists of the valves like a inlet valve and exhaust valve, which is to be accommodated inside the cylinder. This is the line which is shown at the atmospheric pressure, and this is the intake stroke. Intake stroke naturally it happens spark plug in a spark ignition engine, and then the combustion is over. That is the heat addition is there, and then further we get a expansion stroke. So expansion of is being taking place, and then here at this point the exhaust was down into the exhaust gas, into the power stroke or into the cylinder. They are exhausted to the atmosphere, to the exhaust pipe or to the silencer. The exhaust stroke. So here what happens due to the clearance volume, and this is what the process is there, because at the same time, okay, the when the exhaust also open, and it allows the basically the moving of this exhaust gases from the cylinder, and this process is being also called as the scavenging, and the fresh charge is being inducted, fresh charge is being sucked inside the cylinder. So this is the pressure volume diagram, PV diagram for an SI engine, like a petrol engine is a spark ignition engine, SI engine, and we use this auto cycle in case of the SI engine. So this is regarding the SI engine. Okay, so today we have covered the basically the part of the auto cycle, and the uh, part of the auto cycle and the air standard cycle. So again, I will we have started from the basics of the air standard cycle, the topics or the division of the thermodynamics on the three basic areas, and then we have gone into the details of the auto cycle. We have studied the what type of processes are there in the auto cycle, and then the actual PV diagram for an SI engine and its characteristics of the auto cycle for the basically the thermal properties, thermal efficiencies, then PV diagram, and also we have studied the basic like Boyle's law, like Charles law, and ideal gas equation combined. Um, uh, I think remaining topic are many more in this particular case, like diesel engine, SI engine, and all these things. And the dual fuel cycle is also there, and then finally coming to the gate questions. So so today we will basically the stop here with this that is auto cycle, and we will continue in the next class with the diesel cycle. Okay, so let me stop my screen. Yes. Okay. So I will end the meeting now, and we will continue in the next class. ठीक है.
Thank you, Awari sir. Thank you for this nice session.